Okay, so all the equations you see at the top there are on Appendix I, so you don't have to memorize them. And we also have two versions of Planck's constant. This one in kilojoules seconds per mole, and the other one is in joules times seconds per one particle. All right, so the first problem here is calculate the wavelength of light released when an electron falls from the second to the first energy level. So the first step is to convert or to calculate the energy change. So we're falling from the second to the first. When an electron falls, it gives off energy. So from the second to the first. So the final level is negative 1310 kilojoules per mole minus a negative 327.5. So that means my energy change is going to be $1,600. Nope, that's wrong. $982.5 kilojoules per mole. All right. The second step is to then use the next equation to solve for wavelength. So I know my energy. Sorry, that's a negative value right there. Now, I can't plug a negative energy into here. So the way you convert delta E into E is by taking the absolute value. So that means the energy that gets plugged in will be actually a positive value. I'm going to do my algebra. Then I'm going to divide by E. So now I've got my equation, lambda is equal to hc over E. So now I'm going to take my 3.99 times 10 to the negative 13th kilojoules times seconds per mole. And I'm going to divide that by my energy. Again, it's a positive number. And multiply by my speed of light on the top. And when I do that, I will get a wavelength of 1.2 times 10 to the negative second meters, because the unit on wavelength is always meters. So then it asks in part B, what type of light is this? Well, there are 8 forms of light, so you got a 1 out of 8 chance, or you could go down to Appendix I and look for it. Now, I would like you to write the following numbers on your appendix. So this is, it might be hard to see, but that's 10 to the negative 8th, and that's 10 to the negative 6th. So that means 10 to the negative 7th would fall right in the middle there, all right? Now, up here, it's written in nanometers. If we wrote it in meters, it'd be 10 to the negative 7th meters here, and this would be 7 times 10 to the negative 7th meters there, which means that this would be 6 times 10 to the negative 7th, and this would be 5.00 times 10 to the negative 7th meters. So please write those numbers in on your sheet. You should be able to just kind of do this in your head, but you can write it on your sheet anyhow. So the answer from number 1 was 1.2 times 10 to the negative 7th. Well, here's to the negative 7th. Here's 4 times -7. So that means this value must be further along the scale. In other words, it must be somewhere right about here. So the type of light being produced is ultraviolet. And some of you already told, but if you're above violet, guess what? You're ultraviolet. If you're below red, you are infrared. All right. So let's go back up, start on number 2. All right, how much energy is produced by 1 mole of gamma rays with a frequency of 6.8? So I got my frequency. I'll calculate my energy. Now there's only one equation that's got E and F in it, and it's right here. Okay? So again, the reason why I have you write down all the info is because it helps you pick the correct equation. Now, I don't have to do any algebra because I'm solving for E and it's already solved for E. So that means I can just plug in the numbers. Since it's 1 mole of gamma rays, I'm going to use the 1 mole okay, and then when I plug it into my calculator, I will get 271 kilojoules per mole. So I've got 2 sig figs here, so I should round my answer to 2 sig figs, so it should be 270 kilojoules per mole. Number 4, a laser produces a beam of green light with a wavelength of 520 nanometers. Now, I'm just going to go right away and convert that to meters because I know my wavelength has to be in meters. So if I have nanometers up here, I put nanometers down there. I convert to meters. I put a 1 next to the larger unit, and that means the other one will always have a positive exponent. Now, where did I get that times 10 to the 9th? I got that off of Appendix C, because Appendix C says there's that many nanometers in a meter. We're trying to find energy. And once again, there's only one equation that's got E and lambda in it, and that's this one. So my equation is going to be E equals hc over lambda. Now we multiply, oh no, we're calculating the energy. So the energy is already there. So we don't have to do any algebra, that's nice. So we can just go to plug in our numbers. Because it's per mole, I use this Planck's constant. And I multiply it by the speed of light. And then divide by my wavelength, which is going to be 5.20 times 10 to the negative 7th meters. So I'm putting it into the calculator. And I get this big old number out. But since I've got 3 sig figs, 3 sig figs, and 3 sig figs, I will have my answer in 3 sig figs. I have to put the decimal point there so that I have 3 significant figures, and then I, of course, put my units. All right, number 4, a positron is the antiparticle to the electron. It means it's the same in every single way, except it's opposite in charge. So if it's got the same mass as an electron, it would be 9.1 times 10 to the negative 28th grams. Where did I get that number from? Well, I got it from Appendix I. It says right there, that's the mass of the electron. Okay. Then I know the velocity. The velocity is 2.3 times 10 to the 8th meters per second. Now, do not confuse the velocity with the uncertainty in velocity. Okay? So just like if I am going 80 miles an hour and I slow down to 60, my velocity would be 60 miles an hour, but my uncertainty would be 20 because I just slowed down by 20 miles an hour. So your delta, your change, is not the same as the actual velocity. So when I calculate my momentum, the equation that I'm using is P is equal to mv. I'm just going to kind of jump to letter C. When I'm calculating the uncertainty in position, the equation I would use would have the delta V. So just make sure you're being aware of whether you're using V or delta V. So back to 4A. My mass must be in kilograms. So when I convert this to kilograms, I divide by 1,000. And I get okay. What is the wavelength of the positron's wave? Well, I'm looking for wavelength. I know the mass. I know the velocity. Okay. So the equation that I could use is this one. And I could plug everything in there just fine. But a quicker way is to notice that mv is in the denominator, and another name for mv is momentum. So I could just take Planck's constant and divide it by the momentum. And I'm going to do that instead because it's quicker. Now we're only dealing with one positron. And then I'm going to divide it by my answer from part A. And I'm going to get 3.1. Actually, with 2 sig figs, it's going to round to 3.2 times 10 to the negative 12 meters, because wavelength must be in meters. Okay. Number 4 asks you to number 4C asks you to calculate the uncertainty in position. there are two equations that deal with the uncertainty in position. There's this equation, where you plug in the delta V, but there's also this equation. This equation requires you know the change in momentum. So you can use either equation on a test. You just have to look at the information and see, okay, what do I have the information for? Do they give me a delta V? In that case, I'll use this one. If they give me a delta P, in this case, I'll use that one, okay? So in this particular problem, I'm given a delta V. And the delta V is 1.2 times 10 to the 6th meters per second. Therefore, I'm not going to use this equation. I'm just going to get rid of that one. Now I have to solve for delta x. So I'm going to divide both sides by m delta v. Then I can plug in my numbers. This is still for only one positron. Divided by 4, divided by pi. Now my mass, I go all the way back up here to get my mass. It must be in kilograms. And then I multiply it by my change in velocity, which is 1.2 times 10 to the 6th meters per second. And then I plug it into my calculator. I get 4.83 times 10 to the negative 11th. Oh, actually, I should have two sig figs, so it'll just be 4.8, and my units are meters. Okay? I do want to double check to make sure that's the right answer, because it's easy to plug it in. Yep, that's the right answer. All right, number 5. How much energy could theoretically be produced if we converted 10 pounds of uranium into pure energy? Well, I'm going to write down my mass. 10 pounds. First thing we might as well do is convert it into kilograms, because mass must always be in kilograms. Comes out to be 4.5 kilograms. And I'm trying to find energy. So there's only one equation that's got E and M in it, and it's that one. So I plug in my mass. And then that much energy, and it's in joules, okay? Now, I've said in class many times, the wattage is how fast you are spending your energy. So if something is 5 watts, it means you're using 5 joules every second. If something is 75 watts, it means you're using 75 joules every second. So if I've got this much energy, I'm spending it at a rate of 5 joules every second. Now, I can convert 60 seconds into 1 minute, and 60 minutes into 1 hour, and 24 hours into 1 day, or 365 days into 1 year. I could do that and get the same answer, but instead of doing that whole thing, it's just easier to know that there are 3.16 times 10 to the 7th seconds in 1 year. So it's a lot faster doing it that way. And I get, whoop, I put that in the calculator wrong. .6 times 10 to the 9th years. Yep. So that's your test. And like I said, if you want to do more practice problems, you could always do quantum worksheet number 2.